A catalytic converter is a vehicle emissions control device that converts toxic pollutants in exhaust gas to less toxic pollutants by catalyzing a redox reaction. Catalytic converters are used in internal combustion engines fueled by either petrol or diesel including lean burn engines. The first widespread introduction of catalytic converters was in the United States automobile market. Manufacturers of 1975 model year equipped gasoline-powered vehicles with catalytic converters to comply with the U.S. Environmental Protection Agency's stricter regulation of exhaust emissions. These are Euro 0808 Euro converters combined carbon monoxide with unburned hydrocarbons to produce carbon dioxide and water. In 1981, two-way catalytic converters were rendered obsolete by a Euro 03 Euro converters that also reduce oxides of nitrogen. However, two-way converters are still used for lean burn engines. Although catalytic converters are most commonly applied to exhaust systems in automobiles, they are also used on electrical generators, forklifts, mining equipment, trucks, buses, locomotives, motorcycles, and airplanes. They are also used on some wood stoves to control emissions. This is usually in response to government regulation either through direct environmental regulation or through health and safety regulations. History: the catalytic converter was invented by Eugene Houdry, a French mechanical engineer and expert in catalytic oil refining who lived in the U.S. around 1950. When the results of early studies of smog in Los Angeles were published, Houdry became concerned about the role of smokestack exhaust and automobile exhaust in air pollution and founded a company, Aussie Catalyst. Houdry first developed catalytic converters for smokestacks called CATs for short. Then he developed catalytic converters for warehouse forklifts that used low-grade non-leaded gasoline. Then in the mid-1950s he began research to develop catalytic converters for gasoline engines used on cars. He was awarded United States Patent 2,742,437 for his work. Widespread adoption of catalytic converters didn't occur until more stringent emission control regulations forced the removal of the anti-knock agent, tetraethyllead, from most gasoline, because lead was a catalyst poison and would inactivate the converter by forming a coating on the catalyst's surface, effectively disabling it. Catalytic converters were further developed by a series of engineers including John J. Mooney and Carl D. Keith at the Engelhard Corporation, creating the first production catalytic converter in 1973. Dr. William C. Pfeffel developed a catalytic combustor for gas turbines in the early 1970s, allowing combustion without significant formation of nitrogen oxides and carbon monoxide. Construction. The catalytic converter's construction is as follows: the catalyst support or substrate. For automotive catalytic converters, the core is usually a ceramic monolith with a honeycomb structure. Metallic foil monoliths made of canthal are used in applications where particularly high heat resistance is required. Either material is designed to provide a large surface area. The cordierite ceramic substrate used in most catalytic converters was invented by Rodney Bagley, Erwin Lackman and Ronald Lewis at Corning Glass, for which they were inducted into the National Inventors Hall of Fame in 2002. The washcoat. A washcoat is a carrier for the catalytic materials and is used to disperse the materials over a large surface area. Aluminum oxide, titanium dioxide, silicon dioxide, or a mixture of silica and alumina can be used. The catalytic materials are suspended in the washcoat prior to applying to the core. Washcoat materials are selected to form a rough, irregular surface, which greatly increases the surface area compared to the smooth surface of the bare substrate. This in turn maximizes the catalytically active surface available to react with the engine exhaust. The coat must retain its surface area and prevent sintering of the catalytic metal particles even at high temperatures. The catalyst itself, most often a mix of precious metals. Platinum is the most active catalyst and is widely used, but is not suitable for all applications because of unwanted additional reactions and high cost. Palladium and rhodium are two other precious metals used. Rhodium is used as a reduction catalyst. Palladium is used as an oxidation catalyst, and platinum is used both for reduction and oxidation. Cerium, iron, manganese and nickel are also used, although each has limitations. Nickel is not legal for use in the European Union because of its reaction with carbon monoxide into toxic nickel tetracarbonyl. Copper can be used everywhere except North America, where its use is illegal because of the formation of toxic dioxin. Types: 2A. A two-way catalytic converter has two simultaneous tasks: oxidation of carbon monoxide to carbon dioxide, 2CO plus O2 or 2CO2, oxidation of hydrocarbons to carbon dioxide and water, CXH2X plus 2 plus, 3X plus 1 closing round bracket over 2, O2 or XCO2 plus H2O. This type of catalytic converter is widely used on diesel engines to reduce hydrocarbon and carbon monoxide emissions. They were also used on gasoline engines in American and Canadian market automobiles until 1981. Because of their inability to control oxides of nitrogen, they were superseded by three-way converters. Three-way catalytic converters have the additional advantage of controlling the emission of nitrogen oxides, in particular nitrous oxide, a greenhouse gas over 300 times more potent than carbon dioxide, a precursor to acid rain and currently the most ozone-depleting substance. Technological improvements including three-way catalytic converters have led to motor vehicle nitrous oxide emissions in the U.S. falling to 8.2% of anthropogenic nitrous oxide emissions in 2008, from a high of 17.77% in 1998. Since 1981, three-way catalytic converters have been used in vehicle emission control systems in the United States and Canada. Many other countries have also adopted stringent vehicle emission regulations that in effect require three-way converters on gasoline-powered vehicles. The reduction and oxidation catalysts are typically contained in a common housing, however in some instances they may be housed separately. A three-way catalytic converter has three simultaneous tasks: reduction of nitrogen oxides to nitrogen and oxygen, 2-NOx-XO2 plus N2, oxidation of carbon monoxide to carbon dioxide, 2CO plus O2 or 2CO2, oxidation of unburned hydrocarbons to carbon dioxide and water, CXH2X plus 2 plus, 3X plus 1 closing round bracket over 2, O2 or XCO2 plus H2O. These three reactions occur most efficiently when the catalytic converter receives exhaust from an engine running slightly above the stoichiometric point. This point is between 14.6 and 14.8 parts air to 1 part fuel, by weight, for gasoline. The ratio for autogas, natural gas and ethanol fuels is each slightly different, requiring modified fuel system settings when using those fuels. In general, engines fitted with three-way catalytic converters are equipped with a computerized closed-loop feedback fuel injection system using one or more oxygen sensors, though early in the deployment of three-way converters, carburetors equipped for feedback mixture control were used. Three-way catalysts are effective when the engine is operated within a narrow band of air-fuel ratios near stoichiometry, such that the exhaust gas oscillates between rich and lean conditions. However, conversion efficiency falls very rapidly when the engine is operated outside of that band of air-fuel ratios. Under lean engine operation, there is excess oxygen and the reduction of NOx is not favored. Under rich conditions, the excess fuel consumes all of the available oxygen prior to the catalyst, thus only stored oxygen is available for the oxidation function. Closed-loop control systems are necessary because of the conflicting requirements for effective NOx reduction and HC oxidation. The control system must prevent the NOx reduction catalyst from becoming fully oxidized, yet replenish the oxygen storage material to maintain its function as an oxidation catalyst. Three-way catalytic converters can store oxygen from the exhaust gas stream, usually when the air-fuel ratio goes lean. When sufficient oxygen is not available from the exhaust stream, the stored oxygen is released and consumed oxide. A lack of sufficient oxygen occurs either when oxygen derived from NOx reduction is unavailable or when certain maneuvers such as hard acceleration enrich the mixture beyond the ability of the converter to supply oxygen. Unwanted reactions can occur in the three-way catalyst. such as the formation of odoriferous hydrogen sulfide and ammonia. Formation of each can be limited by modifications to the washcoat and precious metals used. It is difficult to eliminate these byproducts entirely. Sulfur-free or low-sulfur fuels eliminate or reduce hydrogen sulfide. For example, when control of hydrogen sulfide emissions is desired, nickel or manganese is added to the washcoat. Both substances act to block the absorption of sulfur by the washcoat. Hydrogen sulfide is formed when the washcoat has absorbed sulfur during a low-temperature part of the operating cycle, which is then released during the high-temperature part of the cycle, and the sulfur combines with HC. Diesel engines. For compression ignition, the most commonly used catalytic converter is the diesel oxidation catalyst. This catalyst uses O2 in the exhaust gas stream to convert CO to CO2 and HC to H2O and CO2. These converters often operate at 90% efficiency, virtually eliminating diesel odor and helping to reduce visible particulates. These catalysts are not active for NOx reduction because any reductant present would react first with the high concentration of O2 in diesel exhaust gas. Reduction in NOx emissions from compression ignition engines has previously been addressed by the addition of exhaust gas to incoming air charge, known as exhaust gas recirculation. In 2010, most light-duty diesel manufacturers in the U.S. added catalytic systems to their vehicles to meet new federal emissions requirements. There are two techniques that have been developed for the catalytic reduction of NOx emissions under lean exhaust conditions: selective catalytic reduction and the lean NOx trap or NOx adsorber. Instead of precious metal-containing NOx adsorbers, most manufacturers selected base metal SCR systems that use a reagent such as ammonia to reduce the NOx into nitrogen. Ammonia is supplied to the catalyst system by the injection of urea into the exhaust, which then undergoes thermal decomposition and hydrolysis into ammonia. One trademark product of urea solution, also referred to as diesel exhaust fluid, is Adblue. Diesel exhaust contains relatively high levels of particulate matter, consisting in large part of elemental carbon. Catalytic converters cannot clean up elemental carbon, though they do remove up to 90% of the soluble organic fraction, so particulates are cleaned up by a soot trap or diesel particulate filter. Historically, a DPF consists of a cordierite or silicon carbide substrate with a geometry that forces the exhaust flow through the substrate walls, leaving behind trapped soot particles. Contemporary DPFs can be manufactured from a variety of rare metals that provide superior performance. As the amount of soot trapped on the DPF increases, so does the back pressure in the exhaust system. Periodic regenerations are required to initiate combustion of the trapped soot and thereby reducing the exhaust back pressure. The amount of soot loaded on the DPF prior to regeneration may also be limited to prevent extreme exotherms from damaging the trap during regeneration. In the U.S., all on-road light, medium and heavy-duty vehicles powered by diesel and built after January 1, 2007, must meet diesel particulate emission limits. That means they effectively have to be equipped with a two-way catalytic converter and a diesel particulate filter. Note that this applies only to the diesel engine used in the vehicle. As long as the engine was manufactured before January 1, 2007, the vehicle is not required to have the DPF system. This led to an inventory run-up by engine manufacturers in late 2006 so they could continue selling pre-DPF vehicles well into 2007. During the regeneration cycle, most systems require the engine to consume several gallons of fuel in a relatively short amount of time in order to generate the high temperatures necessary for the cycle to complete. This has been shown to adversely affect the overall fuel economy of vehicles equipped with DPF systems, especially in vehicles that are driven mostly in city conditions where frequent acceleration requires a larger amount of fuel to be burned and therefore more soot to collect in the exhaust system. Lean burn spark ignition engines. For lean burn spark ignition engines, an oxidation catalyst is used in the same manner as in a diesel engine. Emissions from lean burn spark ignition engines are very similar to emissions from a diesel compression ignition engine. Installation. Many vehicles have a close-coupled catalytic converter located near the engine's exhaust manifold. This unit heats up quickly due to its proximity to the engine, and reduces cold engine emissions by burning off hydrocarbons from the extra-rich mixture used to start a cold engine. When catalytic converters were first introduced, most vehicles used carburetors that provided a relatively rich air-fuel ratio. Oxygen levels in the exhaust stream were generally insufficient for the catalytic reaction to occur efficiently, so most installations included secondary air injection, which injected air into the exhaust stream to increase the available oxygen and allow the catalyst to function. Some three-way catalytic converter systems have air injection systems with the air injected between the first and second stages of the converter. As in the two-way converters, this injected air provides oxygen for the oxidation reactions. An upstream air injection point, ahead of the catalytic converter, is also sometimes present to provide oxygen during engine warm-up, which causes unburned fuel to ignite in the exhaust tract before reaching the catalytic converter. This reduces the engine runtime needed for the catalytic converter to reach its light-off, or operating temperature. Many newer vehicles do not have air injection systems. Instead, they provide a constantly varying air-fuel mixture that quickly and continually cycles between lean and rich exhaust. Oxygen sensors are used to monitor the exhaust oxygen content before and after the catalytic converter, and this information is used by the electronic control unit to adjust the fuel injection so as to prevent the first catalyst from becoming oxygen-loaded while ensuring the second catalyst is sufficiently oxygen-saturated. Damage. Catalyst poisoning occurs when the catalytic converter is exposed to exhaust containing substances that coat the working surfaces, encapsulating the catalyst so that it cannot contact and treat the exhaust. The most notable contaminant is lead, so vehicles equipped with catalytic converters can be run only on unleaded fuels. Other common catalyst poisons include fuel sulfur, manganese, and silicon, which can enter the exhaust stream if the engine has a leak that allows coolant into the combustion chamber. Phosphorus is another catalyst contaminant. Although phosphorus is no longer used in gasoline, it was until recently widely used in engine oil and to wear additives such as zinc dithiophosphate. Beginning in 2006, a reduction of phosphorus concentration in engine oils was mandated. Depending on the contaminant, catalyst poisoning can sometimes be reversed by running the engine under a very heavy load for an extended period of time. The increased exhaust temperature can sometimes liquefy or sublimate the contaminant, removing it from the catalytic surface. However, removal of lead deposits in this manner is usually not possible because of lead's high boiling point. Any condition that causes abnormally high levels of unburned hydrocarbons raw or partially burnt fuel to reach the converter will tend to significantly elevate its temperature, bringing the risk of a meltdown of the substrate and resultant catalytic deactivation and severe exhaust restriction. Vehicles equipped with OBDI diagnostic systems are designed to alert the driver to a misfire condition by means of flashing the check engine light on the dashboard. Regulations. Emissions regulations vary considerably from jurisdiction to jurisdiction. Most automobile spark ignition engines in North America have been fitted with catalytic converters since 1975, and the technology used in non-automotive applications is generally based on automotive technology. Regulations for diesel engines are similarly varied, with some jurisdictions focusing on NOx emissions and others focusing on particulate emissions. This regulatory diversity is challenging for manufacturers of engines, as it may not be economical to design an engine to meet two sets of regulations. Regulations of fuel quality vary across jurisdictions. In North America, Europe, Japan and Hong Kong, gasoline and diesel fuel are highly regulated, and compressed natural gas and LPG are being reviewed for regulation. In most of Asia and Africa, the regulations are often lax. In some places sulfur content of the fuel can reach 20,000 parts per million. Any sulfur in the fuel can be oxidized to SO2 or even SO3 in the combustion chamber. If sulfur passes over a catalyst, it may be further oxidized in the catalyst, that is, SO2 may be further oxidized to SO3. Sulfur oxides are precursors to sulfuric acid, a major component of acid rain. While it is possible to add substances such as vanadium to the catalyst wash coat to combat sulfur oxide formation, such addition will reduce the effectiveness of the catalyst. The most effective solution is to further refine fuel at the refinery to produce ultra-low sulfur diesel. Regulations in Japan, Europe and North America tightly restrict the amount of sulfur permitted in motor fuels. However, the direct financial expense of producing such clean fuel may make it impractical for use in developing countries. As a result, cities in these countries with high levels of vehicular traffic suffer from acid rain, which damages stone and woodwork of buildings, poisons humans and other animals, and damages local ecosystems, at a very high financial cost. Negative aspects: some early converter designs greatly restricted the flow of exhaust, which negatively affected vehicle performance, drivability, and fuel economy. Because they were used with carburetors incapable of precise fuel-air mixture control, they could overheat and ignite flammable materials under the car. While removing a modern catalytic converter in new condition will net only a very small increase vehicle performance, the removal of a 6-year-old modern catalyst resulted in a 3.4% increase in horsepower to many performance enthusiasts. This modest increase in power for very little cost encourages the removal or gutting of the catalytic converter. In such cases, the converter may be replaced by a welded-in section of ordinary pipe or a flanged test pipe ostensibly meant to check if the converter is clogged by comparing how the engine runs with versus without the converter, which facilitates reinstallation of the converter in order to pass an emission test. In many jurisdictions, it is illegal to remove or disable a catalytic converter for any reason other than its direct and immediate replacement. In the United States, for example, it is a violation of Section 203(a)(3)(a) of the 1990 Clean Air Act for a vehicle repair shop to remove a converter from a vehicle, or cause a converter to be removed from a vehicle, except in order to replace it with another converter, and Section 203(a)(3)(b) makes it illegal for any person to sell or to install any part that would bypass, defeat, or render inoperative any emission control system, device, or design element. Vehicles without functioning catalytic converters generally fail emission inspections. The automotive aftermarket supplies high-flow converters for vehicles with upgraded engines, or whose owners prefer an exhaust system with larger than stock capacity. Warm-up period: vehicles emit most of their pollution during the first 5 minutes of engine operation before the catalytic converter has warmed up sufficiently to be effective. In 1999, BMW introduced an electrically heated catalyst, which they called e-Cat, in their 750i sedan. Heating coils inside the catalytic converter assemblies are electrified just after engine start, bringing the catalyst up to operating temperature very quickly to qualify the vehicle for low-emission vehicle designation. Environmental impact: catalytic converters have proven to be reliable and effective in reducing noxious tailpipe emissions. However, they also have some shortcomings and adverse environmental impacts in production. An engine equipped with a 3-way catalyst must run at the stoichiometric point, which means more fuel is consumed than in a lean burn engine. This means approximately 10% more CO2 emissions from the vehicle. Catalytic converter production requires palladium or platinum. Part of the world's supply of these precious metals is produced near Norilsk, Russia, where the industry has caused Norilsk to be added to Time magazine's list of most polluted places. Theft: because of the external location and the use of valuable precious metals including platinum, palladium, rhodium, and gold, converters are a target for thieves. The problem is especially common among late-model trucks and SUVs, because of their high ground clearance and easily removed bolt-on catalytic converters. Welded-in converters are also at risk of theft, as they can be easily cut off. Thieves' techniques for fast removal of a converter, for instance using a portable reciprocating saw, can often damage other components of the car. Damage to components like wiring, or a fuel line, can have dangerous consequences. Rises in metal costs in the U.S. during recent years have led to a large increase in converter theft. A catalytic converter can cost well over $1,000 to replace. Diagnostics: various jurisdictions now legislate onboard diagnostics to monitor the function and condition of the emissions control system, including the catalytic converter. Onboard diagnostic systems take several forms. Temperature sensors are used for two purposes. The first is as a warning system, typically on two-way catalytic converters such as are still sometimes used on LPG forklifts. The function of the sensor is to warn of catalytic converter temperature above the safe limit of 750 °C. More recent catalytic converter designs are not as susceptible to temperature damage and can withstand sustained temperatures of 900 °C. Temperature sensors are also used to monitor catalyst functioning. Usually two sensors will be fitted, with one before the catalyst and one after to monitor the temperature rise over the catalytic converter core. The oxygen sensor is the basis of the closed-loop control system on a spark-ignited rich burn engine. However, it is also used for diagnostics. In vehicles with OBD2, a second oxygen sensor is fitted after the catalytic converter to monitor the O2 levels. The O2 levels are monitored to see the efficiency of the burn process. The onboard computer makes comparisons between the readings of the two sensors. The readings are taken by voltage measurements. If both sensors show the same output or the rear O2 is switching, the computer recognizes that the catalytic converter either is not functioning or has been removed, and will operate a malfunction indicator lamp and affect engine performance. Simple oxygen sensor simulators have been developed to circumvent this problem by simulating the change across the catalytic converter with plans and pre-assembled devices available on the Internet. Although these are not legal for on-road use, they have been used with mixed results. Similar devices apply an offset to the sensor signals, allowing the engine to run a more fuel-economical lean burn that may, however, damage the engine or the catalytic converter. NOx sensors are extremely expensive and are in general used only when a compression ignition engine is fitted with a selective catalytic reduction converter, or a NOx absorber catalyst in a feedback system. When fitted to an SCR system, there may be one or two sensors. When one sensor is fitted it will be pre-catalyst. When two are fitted, the second one will be post-catalyst. They are used for the same reasons and in the same manner as an oxygen sensor, the only difference is the substance being monitored. See also, catalytic heater, cerium, 3, oxide, NOx absorber, roadway air dispersion modeling, references. Further reading, Keith, C.D., al. U.S. Patent 3,441,381 Apparatus for purifying exhaust gases of an internal combustion engine. April 29, 1969, Lachman, IMAL. U.S. Patent 3,885,977 Anisotropic cordierite monolith. November 5, 1973, Charles H. Bailey. U.S. Patent 4,094,645 Combination muffler and catalytic converter having low back pressure. June 13, 1978, Charles H. Bailey. U.S. Patent 4,250,146 Caseless monolithic catalytic converter. February 10, 1981, Srinivasan Gopalakrishnan. GB 2,397,782 A process and synthesizer for molecular engineering of materials. March 13, 2002, external links, catalytic converter at How Stuff Works, automotive applications of high-temperature insulation wool.